Hello everyone, my name's Logan and welcome back to the lecture hall. This is not a sponsor, but it should be. Guayaki by Yerba Mate. Sponsor me. I like the lemon and the orange ones. Okay, now to our actual video. I'm covering section 11.5, the alternating series test. Now, we first have to ask a question. What in the fuck is an alternating series? Well, it's pretty easy actually. It's a series that goes from positive to negative to positive to negative to positive to negative, and it almost alternates between positives and negatives. I know, big surprise, right? And so it's going to be of the form, the sum of negative 1 to the n, or n minus 1, or n plus 1, times b to the n. And so essentially what this does, where b to the n is going to be a sequence, and a positive sequence at that, where this negative 1 will, as your power changes from even to odd, it'll switch from positive 1 to negative 1 to positive 1 to negative 1 to multiply by your bn term. So we get the alternating series test. If the alternating series, the sum from 0 to infinity, or maybe 1 to infinity, of negative 1 to the n minus 1 times b to the n is equal to b1 minus b2 plus b3 minus b4 plus b5 minus b6, yada yada yada, and bn is greater than 0 for all n. If it satisfies both these properties, 1 and 2, b sub n plus 1 is less than or equal to b sub n for all n, and the limit as n approaches infinity of b sub n equals 0, then our alternating series is in fact convergent. So, what do we know? Well, alternating series, use our test, satisfies both properties, it's convergent. If it only satisfies one property, it's divergent. If it satisfies no properties, it's divergent. Now we can get into an example. Now we have the series negative 1, or I guess the sum of negative 1 to the n minus 1 over n from 0 to infinity. And we know the sum of 1 over n, or I guess the series 1 over n, is divergent. But what about the alternating version of 1 over n? Well, what is it going to be? Well, it's 1 minus 1/2 plus 1/3 minus 1/4, and so on. We're like, okay, cool. We can apply the alternating series test. So, what do we know? Well, we know that 1 over n plus 1 is going to be less than 1 over n for all n. So that satisfies condition 1, right? Because this b sub n plus 1 is going to be less than, the property allows for less than or equal to, but is going to be less than 1 over n, which is our b sub n. So that's condition 1 satisfied. Next, we need to think about the limit. Well, if we take the limit as n approaches infinity of 1 over n, well, this equals 1 over infinity, which equals 0. And then we're like, okay, well, that satisfies condition 2. And then by the alternating series test, we can say this series, the sum from 0 to infinity of negative 1 over 1 over n, is convergent. Now, the last theorem for today is I'm covering the alternating series estimation theorem, and it states if S is equal to the sum from 1 to n of negative 1 to the n minus 1 times b to the n, where b to the n is positive, greater than 0, is the sum of the series, S is the sum of the series, that satisfies conditions 1 and 2 from the previous theorem, b sub n plus 1 is less than or equal to b sub n for all n, and the limit as n approaches infinity of b sub n equals 0, then the approximation, the remainder of the sum, Rn, is equal to s minus Sn, which is going to be less than or equal to b sub n plus 1. So what does this even mean? I don't even know what that means. Well, what it means is that we can get a very good approximation to our sum if we have our alternating series test. We know that for a fact this is going to be the case. So then if, for example, maybe in one of these suggested homework problems that I'm going to be doing in less than 2 minutes, maybe more like 3 minutes, asks, hey, approximate it to 4 decimal places. Well, if you can find where this b sub n is at 4 decimal places, we can see, well, the remainder is going to be less than that number. So then if you find this at 5 decimal places, then our remainder is going to be accurate to 4 decimal places, because s minus s sub n is going to be equal to that remainder, which is less than this b sub n plus 1 term, which is at 5 decimal places. So we can say s sub n is accurate to 4 decimal places. Something like that. Essentially, we can use this to approximate our theorems very well, and as many decimal places out as we would like. So that is all I wanted to cover for the lecture portion of the video. Let's transition to some practice problems. So now we look at this series, this negative 2/5 plus 4/6 minus 6/7 plus 8/8, minus 10/9. And we're like, okay, does this series converge? And we also might want to try to figure out what the series even is in the first place. But it's not super necessary, but this would actually be the sum of negative 1 to the n over 2 to the n plus 4. And this would be our sum, right? Because we see this goes up by 2 every time, this goes up by 1 every time, but it starts at 5, where n equals 1 at the beginning, so then this has to be 1 plus 4 to make 5, and that's 2 to the n, or 2n. So we know what our series is, but we didn't even need to do that for actually to test its convergence, because we can see two different things. Well, we could take the limit of this, or we could just look at the terms. And when n is greater than 4, well, our term before is going to be bigger than our term after is going to be bigger than our term before. And actually, that will be the case for all these terms. This is about approximately negative 0.4, or I guess the absolute value of this is 0.4. That's 2/3, which is 0.66. So our series is increasing. It's an alternating series, but it's increasing. So by our alternating series test, it is a divergent sequence because it does not satisfy the properties to converge. Now we're going to do number 4, and this gives us the series 1 over ln 3 minus 1 over ln 4 plus 1 over ln 5 minus 1 over ln 6, and you get the point. And we kind of look at it and we're like, okay, well, clearly we have two conditions that it needs to satisfy for convergence. And we know that 1 over ln of n plus 1 is going to be less than or equal to, or is going to be less than, well, first off, we're like, well, is this n plus 1? And we're like, wait, this starts at 3, n starts at 1. Okay, it's not quite n plus 1, so our series is going to be 1 over ln of n plus 2. So then we're like, okay, well, ln of n plus 2, we're going to compare the n plus 1 term and then the n term. So this is going to be n plus 3, and then this is going to be 1 over ln of n plus 2, because this is the n term and this is the n plus 1 term. And what do we notice? Well, the n plus 1 term is in fact less than the n term. So that satisfies condition 1. And then we have our series. We have this 1 over ln of n plus 2. Well, we just have to take the limit of that. We take the limit of n approaches infinity of 1 over ln of n plus 2. Well, that's equal to 1 over ln of infinity plus 2, which is infinity, and ln of infinity is infinity, so we get 1 over infinity, which is equal to 0. And then we're like, oh, perfect, that's both conditions met. Limit equaling 0, the previous term greater than the next term. Boom, we have an alternating series. We can say it's convergent because it beats, or it matches, or it satisfies both conditions. So now we're asked to estimate the series negative 1 to the n minus 1 of n over 8 to the n to 4 decimal points. And we got to think to ourselves, well, first off, is this a convergent series? Well, we actually don't need to know that. Or do we? Let's think back. Well, we think back to the alternating series estimation theorem, and it says it needs to satisfy the same two conditions. And, well, it's going to. 8 to the n is way bigger than n, right? 8 to the n has exponential growth, while n is just linear growth. So that's going to converge to 0, and we see that, well, each term is less than the following term. Or, each term is less than the previous term. So, now we want to estimate it to 4 decimal places. How do we do that? Well, we know that s minus s5 is going to be less than or equal to s6. And why do I bring up those? Well, I jumped the gun a little here, and I was looking at my notes, and I just know that the s6 term is going to be correct to 5 decimal places. So, let's actually show what the numbers are, so that I can, actually show the problem and not mess around. So we have 1/8 minus 2 64ths plus 3 2/16 minus 4 over 4096 plus 5 over 32,768 minus 6 over 262,144. And we look at it, and I looked up beforehand what these are, so you don't see me just into a calculator, obviously. And this is going to equal 0.00002288. And we're like, okay, well this is 0.0000 to 4 decimal places, so we have 4 0 decimal places, and then we have our continue. Well, we know that then s minus s5 is going to be less than or equal to s6, and because s6 is zeros in 4 decimal places, then this s5 will be correct to 4 decimal places, and then the only variation will be at the 5th decimal place mark. So we need to figure out what these 5 terms add up to be. Well, they add up to 0.106849, and then we're like, okay, well, we just need to round to 4 decimal places because we know, based off our alternating series estimation theorem, we can get correct to a certain amount of decimal places. So this series, -1 to the n minus 1 times n over 8 to the n, will be approximately 0.1068. So that is all I wanted to cover in the video today. As always, my name was Logan. Thanks for watching. Have a great day.